Energy in, energy out, energy in, energy out. Mostly, yeah, mostly it's the case, but sometimes we lose energy. It's really just work done to overcome friction. So let's review the conservation of energy law from our last video. We know that it remains constant in a closed system. It can't be created or destroyed, and it seems to be violated by waste energy. When we include that waste energy into our picture, we get that energy total is the sum of the kinetic energy plus the potential energy plus the heat energy. So, where is the energy really going if we're losing energy? It's not really lost. It becomes waste energy. It's a form that we can't really use very well. Physicists consider it a waste because we can't harness it to do more work. Waste energy is ultimately non-mechanical, meaning it can't move things. So we have heat, light as an example, a flash or sustained output of light, or even sound energy dissipates rapidly into heat in the atmosphere. Let's look at a particular system, like lifting a load here with a crane. In the real world, it takes more energy to lift an object than the change in gravitational and potential energy would suggest. If you look here, let's try a 50-kilogram object lifted to a height of 10 meters. If we inputted 5,500 joules of energy to require this lift, how much energy was used to overcome friction? Well, looking at a system, we look at how much would be the ideal amount or the perfect amount if we had no friction. In this case, mg delta H would tell us 4,905 joules of energy would be needed to gain that 10 meters of height. Since we had to put in 5,500 joules, the extra 595 joules must have been needed to overcome friction, work done against friction, whether it's in the pulley or the system, wherever. It's just extra work we had to put in. Let's try to keep an object moving. The work done to keep an object moving at a constant velocity is to convert directly to heat. So in the case of, let's say, a 2-kilogram object pulled along at a constant velocity with a force of 30 newtons, how much work is done against friction as the object is pulled 4 meters? Well, you know, work is force times distance. Work makes me mad. So force times distance tells us 120 joules in. Since this is also the work done against friction, there's no gain in kinetic energy. In other words, to keep it moving at a constant velocity, there must also be a 30 Newton force of friction opposing the motion. We're in equilibrium by definition of constant velocity. So when we have discrepancies in kinetic energy in the real world, we never get 100% of the energy. The difference is what we expect and what gets lost in the environment. So looking here, we got a 4-kilogram object sliding down a plane 2 meters above the ground at its maximum height. The object has a speed of 3 meters per second when it reaches the bottom. How much energy was lost to friction as it slid down the plane? Well, we can use our conservation of energy to help us here. Start with the object at its maximum height. How much energy did the block actually have, and how much would it have had in the perfect or ideal system? So the theoretical Ke at the bottom should be equal to the Pe at the top. The Pe at the top was 78.48 joules, mg delta H. When we look at the actual Ke at the bottom, 1/2 mv squared, we only had 18 joules of energy. So where did the energy go? Well, of course, it went directly into heat, released as heat energy. You know, when things slide and there's friction, they're going to heat up. So that energy is converted directly into heat energy, and that's why the block's not sliding much, much faster. That's really it in terms of energy. It's just keeping track of all of the energy, gang. Always know how much you had at the start and take it to the very end of the problem. That's it for now. See you in class.